From ContainerDays Hamburg, this video is proudly presented by Dux IT.
This is Beyond the Limits. I will walk you through some crazy controller stuff in the next 30 minutes. So let's get started. Before we jump into the topic, let's get a quick raise of hands who is using Kubernetes operators in their clusters. Okay, that's basically everyone. Great. So who has ever implemented a custom controller or operator before? Not as many, but still at least half of the audience. So this talk is for you. Even if you're not familiar with writing controllers, don't worry, I will guide you through it. So let me tell you why this topic is so interesting to me. I work at the Stackit Kubernetes engine team, and we are managing thousands of clusters for our customers. All of this is based on Project Gardener. And without Gardener, this wouldn't be possible. So shout out to all the Gardener folks. And Gardener manages the control planes and all the worker nodes using Kubernetes controllers. So you could say my job is about running controllers at scale. So this is why I chose the topic for my master's thesis, which was called Horizontally Scalable Kubernetes Controllers. And this is what I will present today. Before we jump into scaling controllers, let's review some basics. So in the end, Kubernetes controllers are there to facilitate a declarative state management so that you can just apply some YAML and the controller takes care to implement the desired state that you want to have. For this, it watches the objects at the API server for changes like spec updates. And if it receives a watch event from the API server, it stores the current state of the object in memory. If there were any relevant changes, like a spec change, it will enqueue the object so that it is reconciled. During this, it first reads the current state from the memory cache, ideally, so that we don't put as much load on the API server. And if necessary, it performs any changes like scaling a deployment, creating new pods, etc. Typically, the controller also reports the observed status, like in the status section of an object, or it might also be an event on the object. Okay, let's see this in action. I brought the web hosting operator, and I will use it throughout the whole talk in my demos. So let's check it out. Okay, great. I hope you can see it. Otherwise, please speak up. So the web hosting operator is running in my cluster. And the basic idea is that we can apply some website object, and it will manage this website for us. But because at the end, there's no better way to run Nginx than on Kubernetes. So let's create some of those websites. In our project namespace, the websites should be ready. I created one for ContainerDays. It's obviously using the exciting theme because ContainerDays is very exciting to me. And the library is probably not so interesting, so it uses the lame theme. Themes are basically a way to configure a color and a font family for our websites. So in the end, for every website, there will be a deployment, an ingress, and a service for exposing the website. So I should be able to open the website I just created using the web hosting operator. Welcome to ContainerDays, everybody. Great. Let's jump back to the slides. So what's the problem? Why are we talking about this? Kubernetes controllers need to prevent conflicting actions between multiple instances of a controller. So if you have two instances of a controller, they typically perform a process called leader election so that only a single instance is active all the time. This prevents that both controllers act independently on objects and perform conflicting actions. With this, Kubernetes controllers are not horizontally scalable. You can't just add another instance to increase performance or capacity of the system. You can only scale them vertically. With this, large-scale use cases, like the one I'm working on at Stackit and with Gardener, are limited. And for now, there is no standard solution out there. And that's why I try to solve this problem and spend my master's thesis on it. I will also show the leader election in action so that we know what we are talking about. So in the web hosting system namespace, there's also a lease object, and this one states the active instance that is now responsible for reconciling our objects. So let's put a watch on the lease and the pods. And let's also watch the logs of the web hosting operator so that we can see when objects are reconciled. If we now add a second instance of our controller, there will always be only a single instance active all the time. And this is the one that managed to grab the lease, basically. So if I create another website for a museum, then we see the same instance acts on it. And if we now delete the active instance, the one with D2 something, we can see in the lease object that it changes to another instance, and now this instance is reconciling the objects, as we can see in the logs. Okay, let me prepare the next demo while we jump back to the slides. Okay. So how do we solve this? I came up with a design that applies sharding that we all know from distributed databases to Kubernetes controllers. So databases like Bigtable, Cassandra, Dynamo, they all have some mechanisms that were proven in practice that we can also apply to Kubernetes controllers. For this, the basic is that we dynamically detect the available instances and if they are failing, so that we can perform assignments as well as automatic failovers and rebalancing when new instances come and leave the ring. The assignments of the Kubernetes objects are stored in labels, so no out-of-band communication. It's all pure Kubernetes API machinery, nothing fancy that you don't know. Still, the design prevents concurrent reconciliations in multiple instances. So a single API object is only reconciled by a single controller instance. And this is what we need to prevent. If we remember the leader election, this is about preventing conflicting actions. This design is implemented in a way that you can apply it to your controller today, and I will showcase this later on as well. So let me walk you through the architecture of Kubernetes controller sharding. At the heart of it, we have a controller, but this time we don't only have one controller, we have 3 instances. Every instance creates its individual lease object so that we know which instances are available for assignments. The goal is that every single instance is responsible for a portion of all the Kubernetes API objects. To achieve this, we have a new component. It's called the sharder. The sharder is configured via another custom resource. It's called the controller ring, where we can specify the API object types that our controller is responsible for. Based on the shard leases and the controller ring, the sharder constructs a consistent hash ring that we also know from distributed databases. And during admission, the sharder adds the shard label to every API object that specifies which instance is responsible for this particular object. There's also a controller that reconciles this label whenever a new shard comes or leaves the ring. The last aspect that we need to implement is adding a label selector This one takes care that every controller only watches the objects that it is responsible for and only has those in memory. Okay, let's see this in action. That was quite abstract, don't worry. If my demo is prepared, there should now be the sharder running in my cluster, great. And there should also be a controller ring for our web hosting operator. As we can see, the ring is ready, and there are 3 available shards. We can also verify this by taking a look at the pods and the leases in the web hosting system namespace. Now there are 3 pods and 3 corresponding leases. So every shard created its own shard lease. It references the controller ring by a label, and the sharder recognized that this one is available for sharding. Okay, let's take a look at the controller ring object. So this one specifies a list of resources that the controller is responsible for. In our case, it's the website's resource. And for websites, the controller creates more resources like deployments, config maps, and so on that reference the owning object via an owner reference. So that's why it's called controlled resources. And for all of these resources, the mutating webhook is configured so that when a new object is created that is not assigned to any shard yet, the API server calls the sharder for this specific controller ring and adds a shard label if it is not present yet. And this happens for websites, deployments, and so on. So let's see this in action. When we now recreate the ContainerDays website, we should see that even during the initial create request, the shard label is automatically added by our sharder. I haven't set this in the manifest that I just used to create this object. So now this particular instance is responsible for reconciling it. So it should eventually get ready. Great. Wi-Fi is with me today. Great. Okay. I can also prove that this website is ready again by just opening it in the browser. Great. Let's create some more application websites because we are not here for a minimal scale. And we should see in the project namespace that these are assigned to different instances of the web hosting operator. Should be a fairly equal distribution across the 3 instances. So far, we only had a static amount of shards. Let's bring some disruption in here and remove one of the shards. So we will watch the pods and the leases. And we will also watch the websites to see what happens to them. And now we just scale down our web hosting operator to 2 instances. So now there should be some websites that need to be moved to an available shard. So what happened first was that the shard lease was released, and the sharder recognized that this is not available for sharding anymore. And then we can see in the watch events that all of the websites that were previously assigned to the terminated instance are now moved to other ones. Okay, so let's see what happens if we add a new instance. This process is a bit more involved because we need to coordinate the handover between an active instance and a new instance. That's why there is a train label involved. You will see it in a second. So when we add another instance, a shard lease is created again. The sharder recognizes that this is ready. But now it needs to inform that for some objects, they need to be moved to the new instance. So the web hosting, the sharder first adds the train label, and then the active shards acknowledges this operation by removing the shard. So this is safe that we don't have concurrent reconciliations during this handover process. Okay. So now that we know what Kubernetes controller sharding is about, you might ask yourself, how can I apply this to my own controllers? And I assure you, this is pretty simple. You just have to follow these 5 steps. First of all, let's install the sharding components, just a simple kubectl apply. And then we are ready to configure the controller ring. As we saw in the web hosting operator, it has a list of resources and controlled resources, and it depends on your controller, obviously. After this, we need to make sure that every single controller instance creates its own shard lease, and it needs to point to the controller ring via this label. And the second aspect is that name and holder identity need to be the same. Typically, you would need use the pod name as the shard identity, basically. Most importantly, this one is per instance and not per controller deployment. If you use Go and controller runtime, this is very simple to achieve. You just import my library, and then you configure the controller runtime manager to use this particular lease implementation instead of the usual controller runtime leader election. Next step is to filter our watch cache. We need to watch and reconcile only objects that have the shard label assigned to our particular shard name. Again, if you use Go and controller runtime, this is very simple. You just set up this label selector and pass it to the manager. But obviously, you can also implement this with any other framework or even another programming language. The last step is to handle the train operations that we just saw in the demo. So whenever the train label is added, we need to acknowledge the operation and remove both the shard and the train label. You guessed it, if you use Go and controller runtime, it's very simple. You just wrap the predicate that you have with my library so that we also react on events where the train label is added. And you also wrap the reconciler that has the actual business logic of your controller with the library to handle the removal of the labels. So with this, you don't even need to change anything in your business logic. You just need to import my library, and then you're good to go. To summarize all of this, you can make your controller ready for sharding in, let's say, 50 lines or less if you leave out the documentation comments. In my master's thesis, I also evaluated whether this whole sharding approach actually makes the controllers horizontally scalable by taking some measurements. So I set up load tests to basically increase both dimensions of load on a Kubernetes controller. The first dimension is how many objects are in the system, and the second dimension is how often do these change, like creations, updates, deletions. So as you can see, I put my controller under significant load, and then I observed that the memory usage distributes quite well over the set of available instances. As you can see, the sharded controller has a little bit of overhead in comparison to the singleton controller, obviously because we also need to run the sharder. But the good thing is the sharder's overhead is constant and doesn't depend on the number of objects. Okay. So now that we know we don't consume much more resources, the next thing is to measure the performance of the system. So I defined 2 SLOs for my controller. The first one is that the controller should be very responsive. So whenever creating, updating, or deleting an object, it should act on it pretty soon, at least under a second. And the second SLO is that the object should get ready fast enough, ideally below 5 seconds. So in my experiments, I measured this in the tool via this histogram metric. When you now add multiple instances, you can measure how much load you can put on the system before the SLOs are violated, and then you get the capacity of the system. If you visualize this, you will see that with every added instance, you get a higher capacity for the number of objects and how often they can change. So this is basically perfect horizontal scalability. For every instance, you get more capacity. Cool. So what's new since I last presented this topic at KubeCon? First of all, I reworked the web hosting operator quite significantly so that it doesn't rely on server-side apply anymore. Typical controllers or operator use this create or patch function or create or update. And this one doesn't perform no-op applies or updates, so it spares a lot of API requests and load on the API server. So that's why I tried to make the web hosting operator more realistic with other operators. Then there were several performance improvements. Most importantly, the Sharder was using or was moving and training objects sequentially whenever there is a new instance or a terminated instance. And this caused a severe slowdown in dynamic environments. So when comparing these, we can see that now the Sharder moves the objects concurrently, and this is much faster. We gain a lot of performance that is relevant to dynamic environments. And to evaluate all of this, I added also some experiments to my load testing tool, where it just terminates random instances, and we can see that the SLOs are still met for the controllers. But now on to the more interesting question, what's next? And this is basically the call out to you, to the community, to help, get involved in the project, and start working on the next items on the agenda. Funny enough, only half an hour after my KubeCon talk, someone opened a proposal on the KubeBuilder repository to integrate sharding in KubeBuilder itself. If you don't know, KubeBuilder is a popular framework for building controllers in Go. The maintainers of KubeBuilder outlined that this is a perfect use case for building a KubeBuilder plugin so that it can be maintained independently from the KubeBuilder core implementation. So that would be great to work on. Another, let's say, design limitation of my project is that you currently can't do multi-level partitioning. So if you consider the deployment controller, where you have replica sets and pods, you would need to ensure that all of these are assigned to the same shard so that it knows about all the ready instances and so on. This is not considered yet in the design, but any ideas for solving this are very welcome. Also, I previously deployed the sharded controller as a deployment always. So when we perform a rolling update, the objects are moved back and forth quite significantly. So one idea was to use a stateful stat instead, so that we can stop reshuffling all of the objects during a rolling update, where we always have a one-to-one replacement for every single controller instance. This is not done yet, but could be tried out. And last but not least, this was also a question at KubeCon. Now that we can scale Kubernetes controllers horizontally, can we do it automatically? So let's apply HPA to a Kubernetes controller. Why not? I haven't tried this out so far, but sounds pretty reasonable. Would be great to see if this works. So let me wrap up the talk. My design makes Kubernetes controllers horizontally scalable. The capacity of a Kubernetes controller system is increased by every added instance, so you could say it's perfectly horizontally scalable now. This design can be applied to any controller. You can reuse the Sharder implementation. If you use Go, it's very simple. If you have another programming language, it doesn't take many lines to implement it. I would say the project is ready for usage, and let's collaborate on this in the community, though I wouldn't recommend running it in production just yet, because I haven't either. But let's gather some more real-world experience with it and improve the project from here on so that we can make it ready for production. With that, I'm at the end of my talk. I'm happy to take any questions. And while you enter the questions in the tool, maybe you want to check out the repository and leave a star. Thanks for listening.
Does it happen that sometimes, somehow, some objects get orphaned, and how would that problem get resolved automatically? Or would manually relabeling be required?
Okay, so updates in the number of shards, I guess, is meant by this question. Yeah, so the sharder runs a controller that is triggered on watch updates to the lease shard leases. So whenever a new shard lease gets created or deleted, it knows about it. But it also has a periodic resync, like every 5 minutes or whatever you configure. So if the controller, the sharder somehow misses an update, that should be taken care of by the next periodic reconcile. So in the worst case, you might have like 5 minutes of unresponsive controller for a given set of objects, but it shouldn't be for longer than that.
Okay. The other one is the controller depends on Sharder, which is another CRD, so you might reach scalability issue.
Yeah, so the question is, how do you shard the sharder, right? Yeah, I guess we don't know the limits yet. We would need to try it out. But in the design, I took care to not watch all of the events in the sharder, because it would again face the same scalability limitation, because memory would just explode in the sharder by watching all of the objects. That's why I use an admission webhook, which is much more efficient in terms of adding the labels and so on. So ideally, the scalability limits of the sharder itself should be much higher than the previous limitations of the controller itself. But let's find out where the limits actually are, I guess.
Another great question is there a possibility for a split brain scenario?
Okay, good question. This is why there is this train label, right? So whenever we move an object from one instance to another for rebalancing, we need to make sure that the previous instance stops reconciling it, because then we would have the split brain scenario between the old and the new instance. Therefore, the old instance needs to acknowledge this operation and basically tells the sharder, hey, I'm done with it. I will not touch this object anymore. And thereby we prevent the split brain scenario.
Great. Could the sharding paradigm be directly integrated into the CRD controller operator like Crow?
I don't know Crow, to be honest, but I hope I can still answer the question. Likely, we can integrate this whole sharding mechanism more deeply into frameworks like controller runtime or whatever Crow might be, sorry for that. Maybe we can even integrate it more deeply into Kubernetes itself. Like instead of running a mutating webhook, we might also implement the sharding mechanism into the Kube API server itself, so that we spare the latency of talking to the webhook server. I guess there are options, but for now, I just put the ideas out there to get some experience and see if it actually solves the real problem before starting the hustle to implement all of this upstream with caps and so on, which is a much more slower process than we need for experimenting with the idea.
A tricky question. So at Stack IT, you currently throw compute at the problem, or are you having multiple controller clusters?
Great question. So at StackIt, we don't throw compute at the problem as of now. I would say we don't have the problem yet. So we are expanding quite rapidly, but for now we have not faced this particular scalability limitation. But that's also why I chose the topic for the master's thesis, because there was no pressure behind it to implement it quickly. This was more like an idea of how will this all look like in maybe 3-4 years. What challenges will we need to solve? And that's why I took this topic. But for now, it's not a real-world problem for us just yet.
So you're not throwing compute anymore. Will the sharding controller take part in Hacktoberfest?
I mean, might be a good place to start. As outlined, there are some issues on the repository. If you want to contribute or take this to an event like Hacktoberfest, that would be great. I'm happy to take any ideas from the community or review some pull requests.
Okay, the last question we have so far is, what about Elixir Erlang related to using Go?
Yeah, I haven't touched those yet. Luckily, maybe, I don't know. But as for the concept, it should be applicable to any programming language or any controller framework. So as you saw, the 5 steps are quite simple to implement, and it doesn't necessarily depend on a specific implementation of the controller framework or the programming language. You can apply the same label selector and so on mechanisms in any programming language that you like.
Any last question in the audience? We're quite ahead of the schedule, which is fine, so we have a couple of minutes. If there's any question in the audience, raise your hand. Don't be shy. We won't bite you.
If you have more questions later on, feel free to contact me on LinkedIn or Slack or in the app, or find me somewhere around here. I'm happy to discuss this further. And otherwise, thanks for listening.
Thanks for this talk.
From ContainerDays Hamburg, this video is proudly presented by DAX IT.